Good morning, students. It's the days are starting to progress like molasses. I think as we get into the end of the term, maybe that's a good thing and maybe it's a bad thing. It just seems like the time moves really slowly. But hopefully that will give you a sense of accomplishment that you have time to do what you need. Now, the test number 4 is posted, and like I said, I'm giving you an additional day this week, like I've done in the past. If you would like to go ahead and get your test done by tomorrow, you certainly have that flexibility. But I wanted to be able to give all of my students an extra day of just flexibility if you felt like you needed it. So the same time window will be available until Wednesday at 11 p.m. And I will go ahead and set up a turn in for test number 4 on the Blackboard site so that when you complete, you can go ahead and scan your work and turn that in as was described for test number 4. Again, be aware that the test will cover through Power Series 9.10, Taylor Series, the end section, and also any new material, that is the material in Chapter 10, I've delayed those homework assignments until the end of the week to give you hopefully some time to relax a little. Unfortunately, school is still kicking and we have to be able to stay current with everything, but hopefully this time window for the test will give you enough level of comfort to complete the test to your satisfaction. So I appreciate your attention to that, and just remember that it's not too much longer. All of the hard work will have definitely paid off. So take advantage of that time that you have. Now, what we want to do today, I hope you're enjoying this parametric equation bit because it is kind of interesting. What we're going to do today is talk about the calculus of the parametric equations. So maybe you'll feel like you're actually in a calculus class. But let me just remind you, when it comes to calculus, we are very much tied to algebra, trigonometry, analytic geometry. So those are the building blocks, the tools that we use to do calculus. So let me go ahead and share my screen. Now for this particular section, what we want to do, ladies and gentlemen, is just basically recapture what we call the Cartesian derivative. That is, how can we get the Cartesian derivative from the parametric representation, and then go back and look at some of the ideas from chapter 7 about arc length and surface area and things of that nature that we now want to write in terms of the parametric representation. So like I said before, when you get to calculus 3 and you're doing curve theory, all of this will come back and hopefully be a good introduction to that. So first, let's start with a smooth curve. Now, what we know about the smooth curve is that it's C1 and the X prime and Y prime are not simultaneously 0. And I've been using the kind of convenient notation here. R of t is X of t, Y of t. Now, sometimes we use thetas. I mean, you can use any letter you like, and the t's are very convenient. Thetas are convenient. I like the t's because they're probably easier to write, but it's your choice with that. And so we would have t in some parameter interval. And for the smooth curve, we can assume, which we will often do, that the X prime coordinate is non-zero. This is the smooth part. Lots of times when we do these calculations, we necessarily have to appeal to the smoothness of the curve because it gives us a curve that allows us to do the calculus. And so curves can't be too uh, disheveled, because if they are, we can't really apply the calculus in an effective way. Now, what we'll see here is that when the derivative is non-zero, then we have what we call a one-to-one function. We either have an increasing or decreasing function. And so with that in mind, we have to look at this by saying, okay, the function x of t is invertible. So again, we're using the calculus invertibility hypothesis. Then x of t is invertible. And when we do arc length, we'll assume that x prime is positive. So we can do that without loss of generality. And when we say invertible, this just means that we can actually write t as a function of x. For instance, here, x, let me write this way. We can consider x as a function of t, and likewise, t is a function of x. And that's the shorthand notation we like to use in mathematics. When we have invertibility, we can write in either direction. So by the inverse function theorem, which we used at the beginning of the course, the derivative of t with respect to x is just the reciprocal, appropriately evaluated, of the derivative of x with respect to t. And that's what we use to find the derivatives of the inverse trig functions. So this is the inverse function theorem. So this is an extremely important result, and we're sticking with the Leibniz notation for now, just to make sure that we keep everything straight between the t's and the x's. So y of x can be written as a composition, y of x of t. Now, what we want to do in this particular, oh, well, actually, I want to reverse that. I don't want to, x is my independent variable. So I use my t of x. Need to get the right order. So this is a function of x, and this is a function of x, since t is a function of x. So we use this. This is going to push the calculus forward. So this is utilizing the fact that the inverse function exists. And so this is a composition of differentiable functions. So we can use the chain rule. I know you all are used to not having a class during test week, but since we only have one day during the week, we're kind of set into the regular mode. So it's good that we have the time to get in this lecture, because we need it. Now, when we do this, we apply the chain rule. So y prime of x will now be, we can write this like the Cartesian derivative. This is what we think of as the Cartesian derivative. Cartesian derivative, just like we did in Calculus 1, and we've been doing all along in this class. So that's just the regular y prime of x. And so now, using the chain rule, we'll have dy dt, the derivative of the outer times the derivative of the inner, and dt dx by the chain rule using the Leibniz notation. And now, of course, we can use the fact that dt dx is just the reciprocal of dx dt. You'll use this in curve theory. So that's why I like to do this in Cal 1. When you get to curve theory, you'll do this again when you parameterize by arc length. So this is an important concept. And so now, if you will, this is where we can say, okay, well, if we think in this particular case, be sure to get the t's and the x's. I love math. It certainly tells you what to do. It keeps you on the straight and narrow. So now what we can do, since we are looking at both of these as functions of t, then we can use the prime notation with the t dependence. So now we can write this as y prime of t, where we're looking at the variable that we started with the parameterization or the parametric representation. And then, of course, when we look at this, and you all think I keep writing things backwards, I'm glad I actually know what I'm doing. Here we go. So math is the greatest thing to keep us focused. So again, here we're using this, and Professor Ron needs to write it in the right order. So this will be x prime of t. So what we're seeing, and this should be a little bit surprising, okay? Because when you look at this computation, though it's very simple, it's very steeped in the notation of the chain rule and invertibility of functions. So when you learn about invertibility the first time through, it's probably not very rigorous. And I tend to be very rigorous, keeping the notation straightened out. And of course, I'm very meticulous about it. If I don't write something correctly, then it's clearly that I've got to get that typo fixed, because this notation is essential. So what we're seeing is, if we have a parametric representation of a smooth curve, then we can actually compute the standard Cartesian derivative based upon this ratio of two derivatives. So with the parametric representation, in order to capture the standard Cartesian derivative, we simply take the derivative of the y coordinate divided by the derivative of the x coordinate. And what's nice about this is fairly simple to remember. So you look at that and think, wow, this isn't half bad. And it's not the quotient rule. It's kind of like L'Hopital's rule, where you take the derivative of the numerator, you take the derivative of the denominator, and then pass to the limit. But here we just have to remember to start with the y coordinate in the numerator and the x coordinate in the denominator. So we get what seems to be a fairly straightforward theorem that allows us to capture the standard Cartesian derivative from the parametric representation. Now, you might be thinking that, what if we needed to look at concavity? Usually we don't have to go much higher than this when we're talking about curves. Now, of course, with Taylor's theorem, we just differentiate forever, and we're glad to have infinitely differentiable functions. So let's just try this again. So let's consider y double prime. And let's just use the notation. I was careful to try to keep this notation very consistent, because that's what we have to do in mathematics. And that's why I like to see your work. That's why I like to see that you're writing your mathematics cleanly and correctly, and not looking for perfection. That's certainly not the case. Math requires that you go out on a limb and search for the correct answer, then going back and checking your work. And so that's where putting your work down allows you to assess and to arrive at the finish line with the correct answer. So now we can say this is just the x derivative here of the x derivative. So now again, this is still a function of t because we just computed it right here. And so we can apply the same chain rule again. So this will just be the derivative with respect to t of dy dx, which is that right there, times the derivative of t with respect to x. But we know that this is just 1 over the derivative of x. So what we're doing is we're iterating this. Let me just go ahead and fill this in. This will just be the derivative of t dy dx divided by dx dt. And so now we get the second derivative, so to speak. So this is just what we call y prime of x. So d dt of y prime of x divided by dx dt. And if you like, let's just go ahead and use the prime notation here like we did upstairs, just to make it a little bit more convenient. So we basically iterate the process. We do the process again, where now we're taking the derivative of what we just computed. So we take the t derivative of this, and then by the chain rule, we again have the x derivative of t, which is what? The t derivative of x 1 over that by the inverse function theorem. And so we appear to get something that looks a lot like this. So whatever we get here to get the second Cartesian derivative, we differentiate this result, so it's iterative. It's a recursive process. We differentiate this, and then again divide by the derivative of the x coordinate. So this iterates. So we'll just say inductively, we can write it this way. We can say the nth derivative, like we're doing the Taylor's theorem, will now be, and we'll just cut down by one derivative, n minus 1. So here, the second derivative, we did the t derivative, the first order. So we just cut by 1 inductively. Now you can do dx dt if you want to make it real formal looking. I did that way in the lecture notes. So like I say, when I do proofs and I say, I really want you to know this, what I mean, ladies and gentlemen, is that I want you to be aware of how we do the proofs and understand the logic, so you can apply that logic to doing actual computations that require the knowledge of that theory. Because obviously I can't really test you formally on proofs like we would have like in a face-to-face setting. So when I say know that, I'm saying be familiar with that. It's like when we did the proof of the binomial theorem convergence, we got plenty of practice with utilizing sum indices and the binomial coefficients. The binomial coefficients are certainly very important structure to writing down the binomial series. So again, in the virtual setting, knowing the proof is basically the foundation to do the problems. And again, here, going through this not only apprises you of the chain rule, but the invertibility condition when you have a non-zero derivative. So this result here is usually showcased in a theorem. And my approach is a little bit different from what you'll find in most books because it actually addresses the smoothness in a way that you have to use it. Because we can't, when we integrate curves, ladies and gentlemen, we can't just integrate over non-smooth sections. I mean, that's a problem. And so we have to be familiar where we might have a cusp, or where we might have the fact that the derivative doesn't exist, like an infinite tangent. These things are actually very important. And so to just completely ignore it is to just throw caution to the wind and keep your fingers crossed, which is not the way we do mathematics. Okay, so now that we have a little rubric here, we actually have a recipe. Let's do some computations of Cartesian derivatives. And then what we want to do is talk about tangents, vertical tangents and horizontal tangents, and how we characterize them for the parametric curves. So here's an example. Lots of these I've taken from the WebAssign. There are lots of just standard examples there. And again, once you know how to do them, you're fine. You already know how to do a Cartesian derivative. Let's just practice it with a specific example. So we have r of t is the square root of t in the x coordinate, and then 4t minus 3 in the y coordinate. And what we're asked to do is compute slope, and we know that's the first Cartesian derivative, and concavity, which is the second Cartesian derivative, concavity at t equal 9. Now you're thinking, there's this interplay between, excuse me, the parameter and the x and y coordinate functions. And sometimes we have to address that. And you'll see that in the next problem. So again, we've got the added difficulty of now having a parameter. Now, using what we just derived, we can say now, if you like, dy dx or y prime. Now, just to be on the safe side, if you do y prime, maybe it's best just to write it that way so you don't confuse it with a t derivative. I think context always gives you what you need to know, but let's just be on the safe side for now, or just keep track what you mean when you write these things. So now, just to remind you, this will be y prime of t divided by x prime of t. Now you're thinking, could you just do these separately and do the ratio? Sure, you can do these any way you like, and I often have a little algorithm for that. But let's just go ahead and move this forward. The t derivative here of y will be 4. And then for x, we just use the power rule. We'll get 1/2 t to the negative 1/2. So now, if you like, we can retire the negative and divide by 1/2. That's just 8. So we'll have 4 times 2 t to the positive 1/2, just retiring the negative power, and that gives us 8 t to the 1/2. Now, if we look at this and we think about what we're trying to do in this particular case, for instance, if we want to go ahead and look at the slope, which we can, we've got this Cartesian derivative. So we can say, for instance, dy dx at t equal 9 equals 8 t to the 1/2 evaluated at t equal 9. Or you could just put the coordinates, but we don't really need those since this is all in terms of t. So this will be 8 times the square root of 9, which is 8 times 3, which is 24. Okay, so very standard, very straightforward, but different from what we're used to. Now, let's look at the second Cartesian derivative. So this is y double prime. So now let's recall from the theorem, we have to take the t derivative of y prime divided by x prime. Okay, well, we just computed y prime, and that's right here. So now we'll just use the power rule. So for instance, if you like, just to make this a little bit, let me just go ahead and fill all of this in for you. Just write 8 t to the 1/2. Be nice and explicit here, but I always am. And d dt. So all the work is right in the computation, t to the 1/2. So now when we take the ratio of the derivatives, first we compute the derivatives. So this will be 8 times 1/2 t to the negative 1/2. And then we have 1/2 t to the negative 1/2. Now, everything goes away. The 1/2's absorbed, the t to the minus 1/2's absorbed, as long as t is not equal to 0. We don't want to do that. And so then we just are left with 8. So in this particular situation, we see at t equal 9, we have a positive second derivative. Here, we're thinking, we've got an increasing curve, increasing as far as the actual Cartesian derivative graph rising. And here, this implies, we'll just go ahead and do a little summary. We'll say R of t is increasing. And we can, and increasing in the sense, we don't usually say increasing at a point, but let me state it this way, so it actually makes more sense. So we've got a positive Cartesian derivative at t equal 9. And in the interval, we think increasing. And then we have a positive second derivative at t equal 9. And we think upward concavity. So again, when we think about concavity increasing, decreasing, we think over a set of content, not necessarily so much at a point. So basically, WebAssign is asking you to think of that way, like you did in your calculus course. So again, we don't really integrate over one point, that we need a set of content. So the idea here is that when we consider the idea of standard calculus with the Cartesian derivative, what we want to be able to do is to capture or locate that standard Cartesian derivative from the parametric representation. So now you're thinking, okay, this is a pretty powerful result, at least from the context that we don't lose the calculus that we had before. We actually have more calculus that makes the problem more vital to us. That is, we're not, racking our brain trying to figure out how we're going to analyze this curve if we don't really have all the structure that we had previous to it. So what we want to do now is think about maybe tangent lines and where we actually have a bona fide tangent. Where do we have vertical tangents, horizontal tangents, and where would we have a situation like, a pathology, like a cusp or a corner? So I want to just kind of review that, or at least make a summary of this. Say we have a smooth curve. In the case of a smooth curve, we don't have to worry about, at least over a particular interval, that we would have simultaneously 0, x prime and y prime. But at endpoints we could, or at certain. So what I'm basically saying is that if we can't ensure that throughout the interval, we can move to what we call piecewise smooth. Piecewise smooth. So when we say that, this basically is equivalent to saying we could split up, for instance, I into 2 subintervals, say I1 and I2. And say R of t is smooth on I1 and I2, except possibly at endpoints, which we don't really have to worry so much about at endpoints. When we're integrating, we can overlook removable discontinuities in an integral. If they're infinite discontinuities, that's an improper integral. But we will often be looking at curves where there will be a lack of smoothness. And so we integrate between the problem areas, so to speak. And so this is what we want to say. So if we have this kind of condition, where would we know? For instance, if we say R of t will be x of t, y of t, like this, then when would we know that we had, say, for instance, a horizontal tangent? Say a horizontal tangent in the sense of the Cartesian. Well, if we know, and let's just remind ourselves, the Cartesian derivative, this is really nice, some very elegant mathematics. And I always say, well, this is a favorite thing to teach. Well, it's all favorite to me because there's such a richness of theory and application to STEM that never gets old. I mean, this is truly beautiful work, and will be around long after we're forgotten. So you have to make your mark now. So when you have a horizontal tangent, what's going to happen is that if we're thinking this is a Cartesian, we need the y prime to be 0. So we will say y prime of the parameter is 0, but x prime is non-zero. Because if we have simultaneously 0, we may have a pathology like a cusp or a corner. And so we don't want that. We want a bona fide horizontal tangent. So we need these two restrictions, so to speak. So when you get the simultaneously 0, that's a problem area. And that doesn't fall into this category. Now, what about the vertical tangent? So now that we have this nice little theorem here, we can characterize these in a way that's pretty simple, even though we have a lot more busy work to do than we normally would. For the vertical tangent, we would assume that we would get the division by 0, an undefined slope. So we'd say x prime equals 0, but y prime is non-zero. And so basically, if we have x prime of t equals 0 and y prime equals 0, we think of this as a pathology. We think of cusps, corners, things like that. And we can't just mow over these with integrals. I mean, you can get lucky, but luck is not what you want to base your model on in an engineering class, and luck is not what you want to base your answer on in Professor Ron's Cal 2 class. Unfortunately, mathematics is unforgiving when you refuse to acknowledge what's actually going on in a particular model or problem. So now when we think about horizontal tangents and vertical tangents, we need this recipe, so to speak, which is based upon our Cartesian derivative here. So let's look at some examples of this. You want to take this seriously and don't look at it like, oh, it's just, plotting a few points, eliminate the parameter. Oh, it's simple. Don't look at it that way. It's kind of like thinking translation of axes and conic sections and rotation of axes are simple, not if you don't pay attention to what you're doing. So let's look at an example of this. So in this particular problem here, WebAssign is asking for the equation of the tangent line at a point. So WebAssign is saying compute the equation. Now it feels like we're back in Cal 1. Compute the equation of the tangent line at each point. So this requires a little bit more work. And here's what we have in this case. This problem will use theta. So I'll just go ahead and write out the coordinates from our R of theta, so to speak. So we're thinking, I'll just write this R of theta, but I'll be a little bit more pedantic here. I'll go ahead and write the X here so we can see it. This will be 2 minus 3 cosine theta. Normally, of course, we just leave that out. We know this is the X coordinate. And the Y coordinate is going to be 3 plus 2 sine theta. Now, there are no restrictions here, so we have to abide by our own mathematical understanding when we do problems like this. Now, for the first one, we want the tangent line, number 1, we want at the point -1, 3. So in order to do this, we need the Cartesian derivative. So we're going to have to work backwards. We're not given the parameter value. We've got to figure that out by solving these equations. And of course, this is actually an ellipse. We talked about this last time. If you actually eliminate the parameters here by moving everything with the X's and the Y's and squaring, you get an ellipse. So this is from the last class. And we talked about this at the end. And so we're going to analyze the ellipse for vertical, maybe horizontal, maybe standard tangent line equations. So now, what does this mean? So we get to do Professor Ron's trigonometry, which is, again, a favorite. So we have what? -1 equals 2 minus 3 cosine theta. So if you will, you can just bring this over. We'll have 3 cosine theta equals 3. So cosine theta will equal 1. Now, of course, when you look at this, we can restrict, but we'll just think about finding a common parameter value for the X equation and the Y equation. So you don't have to beat yourself up, but we know that at least for the inverse cosine function, this answer would be 0. That is, we would say inverse cosine of 1, and that's 0 because we know the inverse cosine lives between 0 and pi. And then, of course, if we extended this would just be all multiples of 2 pi, all integer multiples of 2 pi. So that's good. So when we look at a problem like this, you can also think like you're in pre-cal. If you did the extension to all real numbers, you'd have this where k is an integer. And now for y, so it looks like, we're kind of focusing on 0. Let's see if we can get a 0 out of this one. So we have 3 is equal to 3 plus 2 sine theta. Now, of course, the 3's absorbed. So we have 2 sine theta equals 0. Of course, the 2 divide out by 2. So theta is just the inverse sine of 0. Well, we know the inverse sine lives between -pi/2 and pi/2. So this will give us a theta of 0. And then, of course, we can extend to all solutions. These are on the axes. How simple. We don't even need Professor Ron's lemma. So this would just be pi k. Again, I won't repeat k as an integer. I know we've been using n's with the series, but I'll use k's here because it's fairly standard, not to confuse you with the series that we've been doing. So now what we can do is just select, in this case, select theta equals 0. Because obviously there are infinitely many solutions. It's like polar coordinates. We're not getting unique solutions with the trigonometry unless we just stick to the inverse trig function. So again, be flexible. The answers will all work out as long as you're using good trig skills. So now we've got this selection. So let's just see, what's going on here at this point. So now let's look at this. I'll go ahead and do these separately, ladies and gentlemen, then we'll take a ratio. Let's go ahead and look at x prime. x prime will be the derivative of 2 minus 3 cosine theta prime. So the derivative of 2 is 0. And of course, the derivative of cosine is the negative sign made negative. This will just be 3 sine theta. And y prime will just be the derivative of 3 plus 2 sine theta. You have to be a little bit more pedantic with these, because if you're not, like with series, you just start to write down hash, and you don't want to do that. So now this is 0, and of course the derivative of sine is cosine, so it's like we're back in calculus 1. So now this implies that the Cartesian derivative in this case, and if you want to check here, notice, I'll get to that. I'll come back to this. This will be y prime of theta. Now, of course, ladies and gentlemen, instead of the t, we're using the theta. So, just be wary of that if you want to write this in. So this will be 2 cosine theta divided by 3 sine theta. If you like, that's just 2/3 cotangent theta. Or you can just kind of keep in mind that that's how it's built. But now, when we look at this and we think, well, okay, well, what's going on at y prime? Well, in this case, y prime, I'll use good notation. We're so bad in math. Let me show you the horrible notation which we use in Cal 3, and your physics professor does the same. We'll say y prime -1, 3 without using brackets. That's pitiful, but that's what we use. So this would actually be the y prime. Well, let me write it this way, like I did before. We could write this as the dy dx when theta is equal to 0. But now, of course, when theta is equal to 0, this is undefined because we got sine of 0. So we just say undefined. But here's what's interesting. Note x prime of 0 equals 0, but y prime of 0 equals 2, which is not 0. So like we said before, when we do the vertical tangents, we need this, and that's exactly what we have. So this implies vertical tangent. So the equation will just be the vertical line, and we'll say at the x coordinate. So we have x equals -1. So we have a vertical tangent at the point -1, 3. We have a vertical tangent that corresponds to theta equals 0. So the actual vertical tangent has this equation. So again, we have to check several things. These are a little bit long-winded, but that's why you have to be careful when you do these. Now let's look at another one. Let's look at 2,5. This is like doing infinite series because it's a mature level of work that would never work in pre-cal or cal 1. So 2,5, let's do the same thing. So what is this going to mean? Equivalently, we'll have 2 equals 2 minus 3 cosine theta. So remember, everyone, we just go back to our equations that we have up here. So now the 2's absorb, and if you want to take the cosine over, that's just going to be 3 cosine theta equals 0, or cosine theta equals 0. So theta is the inverse cosine of 0. Now, when we think about this, these are on the axes. These are odd multiples of pi/2. So first, we can think about the actual inverse cosine function that lives between 0 and pi, and this would give us pi over 2. But of course, we could write all solutions as, we can write it this way, 2k plus 1, where k is an integer. So this is always odd multiples of pi over 2. That would be all solutions. Okay, so just standard trigonometry. And then, of course, we have 5 equals. So again, 3 plus 2 sine theta. So now, of course, the 2's absorbed. So we get 2, or we get 2 when the 3 absorbs into the 5. So 2 sine theta equals, in this case, 2. So sine theta equals 1. So theta is equal to the inverse sine of 1. And of course, we know that's pi over 2. Now, when you think about a situation like this, you're thinking we're always on the positive y-axis. So pi over 2, 5 pi over 2, 9 pi over 2, 13 pi over 2. So you would say all solutions would have this form. We would say a 4k plus 1. Just your standard trigonometry. So again, when you think about this, we're good to go. We've got a nice agreement here. So we will select theta equal to pi over 2, just a common value. Kind of fun. So now, notice again, recall, that's such a good word in math, recall y prime of x. What is that? We computed that. We get, let me remind myself, where did I write it? 2/3 cotangent theta, or if you like, 2/3 cosine theta sine theta. And so we have the point 2,5 and a corresponding parameter value of pi over 2. So doing the polar coordinates and the parametric, it's like we get to revisit the trig, but that's really ridiculous for me to say that, because what have we been doing all term? A lot of trig. I mean, if we get a little break from it, exactly, just a little break, then you get hit with more trig. So Cal 2 is like trig city. And then of course, you know, the natural logarithm, the exponential functions. I mean, we can't get away from them, can we? So now when you say here, you'll say, okay, well, y prime at 2,5 will just be dy dx for a parameter value of theta equal pi over 2. But now, of course, if we look at this, I can go ahead and write this out. This is cosine. You see, we're going to get a 0. So we get cosine of pi over 2 divided by sine of pi over 2. So that's 0 over 1, again, which is 0. Now, of course, what we're noting here is that x prime, I'll move my notes that I just made, x prime, in this case, of 0 is sine of 0 let's get the right parameter value. That's why I like t's. The thetas remind me of zeros. Pi over 2, sine of pi over 2, which is 1, and y prime of pi over 2, in this case, is cosine of pi over 2, which is 0. So now we have the case where we have the numerator is 0, but the denominator is non-zero. So this implies the horizontal tangent. Again, not a cusp, not a corner, a bona fide horizontal tangent. And you're thinking, That's what happens with the ellipses. You know, you've got the vertical tangents and you have the horizontals when you draw them. You expect this. So this is basically proving what you learned in pre-cal, but you didn't have any of the calculus to support it. And the parametric representation is so nice when you think about the conic section. So such a big plus when you're thinking about curve theory. So now we see here, we have a bona fide horizontal tangent, so we just have y equal to 5. So y equal 5. Okay, so now let's look at the last one, which is kind of interesting. Save the best for last, right? So I need an extra sheet here. So again, I wanted to take this time to kind of get back into the trig and really get you entrenched with the parametric calculus so that you'll be ready for polar coordinates, which will keep you busy also. So now in this case, we have the following point. For the third one, we again want a tangent line, and we have 4 plus 3 root 3 over 2, comma 2. So WebAssign asked us to compute the tangent line here. Again, let me remind you what the curve looks like. 2 minus 3 cosine theta. Y is 3 plus 2 sine theta. And we remind ourselves that the Cartesian derivative, kind of repeating ourselves to make sure we have everything we need, is the 2/3 cotangent theta, which is 2/3 cosine theta over sine theta. And we remember that this is y prime of theta over x prime of theta. When we did the proof, it was x prime of t, y prime of t. So there are lots of things to keep in order, and it's very easy to get careless. So I'm trying to be, like I say, very meticulous about this, just like we're doing series, to keep everything in order. So now we need a parameter value. So let's just see what we have. So we have 2 minus 3 cosine theta equals 4 plus 3 root 3 over 2. So now we can just kind of mix and match. So if you like, we can say -3 cosine theta, and this will be 4 plus 3 root 3 over 2. And of course, go ahead and get a common denominator of 2. So this will be a -4 over 2. Well, WebAssign was good to us because the 4 over 2 and -4 over 2 absorb. So we get a 3 root 3 over 2, -3 cosine theta. So now we can divide here. The 3's absorb, leaving a negative. So cosine theta equals -√3 over 2. Now, of course, the cosine lives between the inverse cosine between 0 and pi. And so this is going to give us the 5 pi over 6. That is pi over 6 in the first quadrant, and then 5 pi over 6 in the second quadrant, where the cosine is negative. So we have theta equals, in this case, 5 pi over 6. But now, of course, by Professor Ron's lemma, there are other zeros too. So we could say, in this case, another alpha or another theta would be 2 pi minus 5 pi over 6. And that would just be a 12 minus a 5. So that gives us a 7 pi over 6, at least in 0 to 2 pi. So that gives us a little bit more flexibility with the parameter value. So again, this is a nice review of your trig, and trig is such a wonderful place to do mathematics. Doing Fourier analysis with sines and cosines is again a favorite because it's just, the trig functions are phenomenal in what we can do with them. So there we go, we got two possibilities. We can extend to all by adding multiples of 2 pi here if you like. So now, excuse me, we have 2, excuse me, equals 3. When I run in the morning and it's cold, I enjoy the cool, but I do get a little raspy. But that's okay. I'm willing to do that. I still have to wrap up my head, but I don't think I do it enough. There we go. So now, if we do this, we'll have a -1. So sine theta is equal, excuse me, -1/2. So now, of course, when we look at this, the inverse sine runs between -π/2 and π/2. So we have theta. And of course, the inverse sine is what? It's odd, so the negative factors. Excuse me, I'll eventually get it cleared. Sorry, I don't mean to gross you out. So inverse sine of π/2 in this, excuse me, of 1/2 will be π/6 made negative. Now we need to mod out, so to speak. So this is congruent to 2 pi minus π/6, which is 11 π/6. But now by Professor Ron's lemma, the other 0 in the lower arc is in the 3rd quadrant. That's in the 4th quadrant. So we say the other 0 is 3 pi minus 11 π/6. So that would be an 18 minus 11, and that gives us the 7 π/6. So we've got a nice parameter value here that we can use. So it takes a little bit more time to figure out a good parameter value, especially when the equations don't mesh up very well. We use our inverse trig functions, and then we mod out using the fact that sine and cosine are not 1-to-1 in 0 to 2 pi, and that's a thorn in our side. You know, it makes it much more difficult to do. And so this is a thorn in the side of my pre-calculus students. So now we've got this parameter value. So let's see what we get. So y prime of, well, that number, let's see here. I'll do it. Like, my goodness. Choose to be consistent, and I am consistent. So if we actually evaluated at that point, this would be dy dx when our parameter value is 7 pi/6. And so of course we get 2/3, and this will be cosine of, go ahead and leave it this way, otherwise we'll just have to reinterpret it anyway. Cosine 7 pi/6, sine 7 pi/6. So we get 2/3. Now, of course, here, the cosine of 7 pi/6, that's going to be a -√3/2. And then, of course, the sine, in this case, of 7 pi/6 is -1/2. So now the 1/2s go away and the negatives go away, and we just get 2/3 times √3. And then, of course, the √3 can absorb into the 3 and give you 2/√3 if you don't want to leave it with all that stuff. Webasine doesn't care if things are not rationalized, and I don't either. Your physics professors don't either. It sometimes is a pain. And it's easier to compute with things like this. So now we're thinking, okay, well, yay, finally, we got something besides the verticals and the horizontals. We've got a non-zero tangent, which is good. So now we're thinking, all right, here's our Cartesian derivative at, in this particular case, this point, and fortunate as it is, corresponding to a parameter value of 7 pi/6. So now the tangent line, and Webasine doesn't care how you do this. They're not specifying a particular form. So I'll just do like, put everything on one side. So now we have y minus 4 plus 3 root 3 over 2 equals 2 over root 3 times x. Oh, sorry. I guess it would help to have the right number here. Y minus 2. Let me write down the number instead of trying to look up there and writing it in the wrong order. So there's the point and there's the slope. So we have y minus 2 and we have x minus 4 plus 3 root 3 over 2. And now, if you will, when we multiply here, and I would say at this point, one thing that's interesting about the computation here is that when we think about what we're doing, we can already go ahead and clean this up and make this a little bit better with that square root there. So now what does this give us? Notice we have the y minus 2. Here we just get the 2x over root 3. And here the 2's absorb, and we get a minus 4 plus 3 root 3 over root 3. Now this is what I was talking about. If you want to clean this up to make it a little bit easier, we can just multiply everything by root 3. So multiply by root 3. So this will give us root 3 y minus 2 root 3 equals 2x minus a 4, and distribute the negative, minus a 3 root 3. Now you can just put everything on one side if you like. Just run everything over here equivalently. So we have 2x minus root 3y plus 2 root 3 minus 3 root 3 equals 0. And then, of course, I've got a minus 4 there that I left out, not to discriminate against the minus 4. Forgive me. And so now these absorb, or I can get a negative root 3 there. So we have equivalently 2x minus root 3 times y minus root 3 minus 4 equals 0. So WebAssign not asking you to do this in any particular form. So I just did the ax plus by plus c equals 0, the form, you know, that we least like, ax plus by plus c equals 0. I'm teaching conic sections now, so I'm thinking of conic sections in this form, even though I don't always state the standard form. I'm just happy that they understand translation of axes. But if we get to rotation of axes and I have time for it, I'll go back to this. So the idea here is that when it comes to computing tangent lines with the parametric representation, it's not always as seamless. I mean, you know, you in Cal 1, you know, you compute your derivative, and as long as the numbers aren't too horrible, you think about the ones that have the trig functions, they tend to be more difficult because you just have more arithmetic to do. But you have to pay attention to what's going on. And then, of course, once you have all of the raw materials, the computation of the tangent line is the same. The point slope is just our window to getting any form that we like. And of course, you could just leave it like this if you want. If you don't, as you work on the test, if you don't want to clean things up, as long as it's a correct response, WebAssign would look at that and give you a nice green check. So I simplified this just to make it look better, but the WebAssign is scanning it for an equivalent response to the correct to a correct response. There's not the correct response. You know, the thing about mathematics is that the exact answer is always preferred. On occasion, we do need an approximation. it serves us well. But the exact is what we look for, and that's what WebAssign can always test for, which makes it a wonderful tool. So now there's another example here before we get to the arc length, where it just says find all points of horizontal and vertical tangency. Okay, so this is kind of like a little bit different from the last, where we just focus on the horizontal and the vertical, the points, not the equations of the lines. So I want you to see the difference. So here we want to find all points of horizontal and vertical tangency. So you're thinking, if you're writing in parametric, you can basically think of the point as being represented by the parameter value or the actual point itself. So sometimes WebAssign will be a little bit more flexible with you. But here we want the point, so that could either mean the actual parameter value or the actual point that you compute with that parameter value, but not the actual equation. So in this case, we have, and I'll write this in a more relaxed setting, we have the vector function basically of theta, and the x is cosine theta plus theta sine theta. I used to say, if you don't like these variables, change them. Not anymore. Stick to the variables with WebAssign because everything has to be coded as the problem is given to you. If you need an auxiliary variable to solve an equation or whatever, that's fine, as long as you maintain the original variables in your response. We often have to do that. So now when you look at an equation like this, just like when we did the epicycloid, we got a really user-friendly form once we did all of that trigonometry. That was a challenging derivation. Certainly something that would be beyond pre-calculus students, but again, more mature students in the Calculus 2 class, because you have that additional background, can understand it. But again, it's very much setting up a scheme that allows you to interpret the theta, and then of course using all those co-function identities. Not a simple thing. So in general, parametric representations are anything but simple. Now, when we do this, we just harken back to the Cartesian derivative. So we know first, let's just go ahead and compute x prime relative to the theta here. So we get a negative sine theta. And then by the product rule, we get plus a sine theta. And then of course we get a theta times a cosine theta. So now the sines absorb and we get theta and cosine theta. And now y prime, when we look at this, we take the derivative, we get a cosine theta. And then of course, the derivative of, well, let me just cover this up. The derivative here is just cosine theta with a negative, so that will absorb. How convenient. And then now the derivative of cosine is the negative sine. And then of course, negative, that'll be plus theta sine theta. So this gives us theta sine theta. Now, again, we want to just do this comparison bit. So before I finish this, let's just remind ourselves, vertical, for the vertical tangent, we have, and I'll just write up here, y prime. This is y prime of theta, x prime theta. So in this case, for the vertical, we have x prime of theta equals 0, y prime of theta is non-zero. And then we have for the horizontal, y prime of theta is 0, and x prime is non-zero. So now what we can do is say, okay, well, let's just think about what we're saying here. So let's set these to 0. So x prime equals 0 if and only if theta equals 0 or cosine theta equals 0. Well, theta equals 0 is kind of fixed. And so theta, oh, and in this particular problem, there is a restriction. And you're thinking, hallelujah, Professor Ron, there's a restriction. And here it is. Theta will live between negative 2 pi and positive 2 pi. So there's a restriction. So that's the WebAssign restriction. I marked that in my notes, but there's the restriction. And so we've got inverse cosine of 0. But of course, we know that's on the x-axis, excuse me, on the y-axis, where we have what? Odd multiples. And then and there was another, let me check something here. There was another example. That was with the sine. Let me check back here. That was with the sine. That was a good example. I want to make the difference here. Notice, right. Remember back here where we had the inverse sine of 1, that was pi over 2 or 5 pi over 2 or 9 pi over 2, where we had 4k plus 1 pi over 2, because we always had to be up here, okay? There's a difference. Now, we want cosine to be 0, so we can either be here or we can be here. That is pi over 2, 3 pi over 2. So you're thinking here, this would just be, if we wrote everything down, this would be, well, here, let me do it this way first. Let's just say pi over 2, because that's what the inverse cosine gives us. Then we could say all, if we extend, will just be 2k plus 1 pi over 2, okay? So again, with the sine being 1, we were just stuck up here. But when cosine is 0, we're either here or here. So there's a subtle difference. So now, when we look at this and then we think relative to this, what are the values of theta? Well, we get a 0, and then we can just start marking them off. Well, when k is equal to 0, we get pi over 2. When k is equal to 1, we get 3, so we get 3 pi over 2. But of course, if k is equal to 2, we get 5 pi over 2, but that's pi over 2 too big. All right, so we stop. So now let's just do the negative. When we have negative 1, we get a negative pi over 2. So that's a negative 2 plus 1. So negative pi over 2. And when k is equal to negative 2, we get a negative 3 pi over 2. And then, of course, we stop, because if we go any further, we're less than negative 2 pi. So that's it for that. So this is where we're getting the, let's just write it, x prime equals 0 right here. So now let's do the y prime. So y prime equals 0 if and only if. Well, let's just look here. Theta is 0 or sine theta is 0. So now, of course, we have 0, that's fixed. But now for 0, of course, we're looking here. We're on the x-axis. That is 0 pi. So we could say theta. What's the inverse sine of 0? Well, technically it's 0. Because again, the inverse sine function lives, I keep saying all of this, I mean, this is pre-cal, but if you ever struggle with the inverse trig functions, go to the Wikipedia page on inverse trig functions. It is wonderful. It is a masterpiece of everything you would like to know about inverse trig functions. I refer my pre-cal students to it because unfortunately in pre-cal you get about this much on inverse trig functions, which is not sufficient. You have to really teach this stuff, and it's a marvelous tool for checking what you know and you know going to, well, I don't remember that identity. Professor Ron used that in class. Let me go back and see if I can find it. Let me go back to his lecture. Sometimes it's easier just to go to the Wikipedia page. So now we can see if we want all, we just want multiples of pi. So let's just go ahead and write these down. So y prime equals 0. Well, first we have theta. We've got the 0 that we had there. And then let's just kind of look through this. If k is equal to 1, we get a pi. If k is equal to 2, we get 2 pi, and that's right on the endpoint there. So that's it. And then, of course, we can go negative 1 for k, just like we're doing series, right? And then negative 2 pi. So then we stop. So now what we can see here, ladies and gentlemen, is that for the vertical, let's say vertical tangents, where will they occur? They will occur, again, the 0, 0 is an issue. That's no good. That's where we got simultaneously 0 and x prime and y prime. So that's a discard there. That's a cusp. So that's a discard. So we don't have anything there. But notice here, we need x prime equal to 0. So otherwise we're good. These don't correspond with any of these. So for the vertical tangents, we get, excuse me, we get the values of theta will be pi over 2, 3 pi over 2, negative pi over 2, and negative 3 pi over 2. And now for the horizontal tangents, where do they occur? And these are points, okay? Points. The horizontal tangents we've got theta. What are the points? So that's going to be what? We need y prime 0, but x prime not equal to 0. So that'll be pi, 2 pi, negative pi, and negative 2 pi. Now what you can do here for all of these values, you can actually go in and write the actual points. And I wrote them down. I wrote all of them down. That is, you'll get pi over 2, 1. These are easy. I just thought I'd list them. Negative pi over 2, negative 1, negative 3 pi over 2, negative 1, and 3 pi over 2, 1. So for instance, if you wanted to do for the, let's see here, we've got vertical right here. Let me just kind of put these all together. So the idea here is that if you replace theta with pi over 2, that's a 0, and then pi over 2 times sine of pi over 2, that's just pi over 2, so that gives you this, the pi over 2. And then of course, with the y, when you do the pi over 2, you get, in this case, a 1, and then you get minus pi over 2 times cosine of pi over 2, which is 0, so you just get the 1. So you're just substituting the values in here into these equations to get the actual Cartesian points. That's all I'm saying there. And so I wrote them down here for the other one, just computed them for the horizontals. You'll get negative 1 pi, -1, negative pi, 1, -2 pi, and 1, 2 pi. Just if you were just interested in the actual Cartesian point. WebAssign only asks for these, but I thought it might be interesting just to go ahead like we did in the previous problem. So for instance here, if you try the pi here, that'll be a -1. And then of course, pi times sine of pi, that's 0. So you get -1 right here. And then when you replace with pi, in this case, you get sine of pi, which is 0. And then you get a negative pi times a cosine of pi, that's a -1. So negative, negative, positive, and you get the pi. So that's how you can generate these actual Cartesian points. So again, WebAssign was just interested in the values of theta. So we can think of the points as being represented either by the actual parameter value or the actual Cartesian coordinates, okay? So remember in the previous example, we were doing tangent lines. Here, we're just interested in where do these vertical and horizontal tangents occur, okay? And avoiding the simultaneous x prime, y prime equals 0. So it's not hard work, ladies and gentlemen. It's just different, and it's just a little bit more tedious to keep up with everything. Now, what we want to do is go ahead and switch out the arc length formula. So what I want to do here is just say, write an arc length formula using parametric representation. Using parametric representation. So what we can do in this particular case is that we can assume, I'll use t's now, r of t, with coordinate functions x of t and y of t, in this particular case. And we're going to say r is smooth. And what I will say here without loss of generality, we'll assume that x prime is positive. So basically here, we're going to move from a Cartesian equation to a Cartesian curve to basically a parametric curve. So I'll just say the Cartesian curve, just set this up, will just be y of x, where x lives between a and b. And for the parametric curve, we'll just say that we have, alpha beta. We'll just say t lives between alpha beta. So just like we were doing these transference between the Cartesian and the parameter, for instance, here, this would be the x Cartesian, and this would be like the value of theta, just like we've been doing for 20 years in the previous problems. Again, now this makes more sense. So now we can say, so this will imply that we have S equals A to B, and I'm going to use the 1/2. So this will be 1 plus dy dx. I'll write it this way, so the Cartesian comes out. Now, again, this is where the theorem about the Cartesian derivative in terms of the parametric is extremely important. So now we can go ahead and fill all of this in. So now this dy dx, and just recall, that's just going to be y prime over x prime. So this will give us alpha to beta 1 plus y prime divided by x prime. Now these are I'll start out with the t, and then I'm going to not write them anymore so we don't go crazy. You know, it's a function of t, and so I'll just write y prime squared after this, just so we don't feel like we have to write forever. Dx. And now we'll get alpha to beta. And this will get a common denominator. And let's see, we'll get, again, we'll have an x prime squared plus a y prime squared divided by the common denominator x prime squared. And I'll bring this down a little bit. Now, one thing that we can notice here, and this might be a little bit simpler to understand, and this is what I've written over here. We can utilize x of t and then just say dx is x prime of t dt. So we'll eventually use that. This is a function of t. So we get alpha, beta, and now we've got what? X prime squared plus y prime squared, 1/2. And then we've got 1 over the absolute value of x prime. Well, now we're going to substitute x prime dt for the dx, which I could have done up here, but I didn't. Now we're going to use that here. And now, of course, by hypothesis, the x prime is positive, so these absorb. So x prime absolute value is x prime by hypothesis. So we're using that by the smoothness. And so these will absorb, and we just get alpha, beta. Now I can write it to make it look a little bit prettier. We'll do x prime of t, too many brackets, squared, plus y prime of t squared, square root dt. So the idea here is that we reframe the standard 1 plus y prime squared now in terms of parametric. And so you get really a formula that can be extended to 3 dimensions and more if you just want to live in 4 space. But basically, you get the Pythagorean deal with the parametric coordinate functions. So you have x prime squared plus y prime squared square root. So this is very Pythagorean and very easy to think about, and it makes the parametric form of the arc length very easy. So again, I'm not trying to be sloppy, but just to write a little less, we just do x prime, and then at the end we can put in the t dependence. The idea is that as we use the differential notation here, we simply replace the x with x prime dt, just using differential that Leibniz gave us. And this gives us our coordinate conversion to t. So now we have a very nice, straightforward arc length setup. So let's use it. So this is easy to remember. So now we did a problem way back. Now that we can recast as a parametric representation, and it was really the star curve or the hypocycloid. So, for instance, I'll just say earlier we studied this particular Cartesian curve. That is, we're going to take a positive, split like this, x over a 2/3 plus y over a 2/3 equals 1. And this had that very interesting star shape. We used a lot of nice analytic geometry. This can be recast in terms of a parametric curve. So let's do our A's. Nice, elegant symmetry here. I mean, it's a nifty little curve. So this is what I was talking about, cusps. We can't just mow over them. We even talked about this before, even when we didn't have parametric. Still, it was still true. Right there. So the idea is that we're thinking, you know, if we want to make a setup here that would be kind of nifty, we can think of a parametric representation like doing an ellipse, so to speak. So we could set up something that would absorb the A. So here we can say, let, now, for instance, X equal, at least for now, we'll just say A cosine theta and Y equal A sine theta. And let's see if this will do what we want it to do. So, so if and only if, let's see, Y over A. So if we look at that and then we say, okay, well, that's almost what we want. Let's look at it this way. Now, let's see here. That might be a good way to do it. Let's try this. Let me also look at it this way. Say, for instance, if X equals A cosine cube theta, let's try this. Maybe this will work a little bit better. Y equal A sine cube theta. And then we'll have X over A equals cosine cubed. And Y over A equals sine cubed. And then let's see here, then we can say, in this particular case, if we square, let's see here, so now, let's see if this will actually give us something that'll work. What I'm trying to do is actually work this backwards. So if we do a square here, and let's see, in this case, let's try this. So let's see here. Oh, I see now. Let's see here. So also looking at that, X over A to the 1/3 will be cosine theta to the 1/3. And then Y over A to the 1/3 will be sine theta to the 1/3. And then squaring X over A to the 2/3 equals cosine theta to the 2/3, and then y over a to the 2/3 will be sine theta to the 2/3. Okay. Then x over a 2/3 plus y over a 2/3. And let's see here, that will be cosine theta. Let me write it this way. So cosine theta squared to the 1/3 plus sine squared theta to the 1/3. Now this is where I actually need a 1, but I need to think about this. This now will give us this, and so if I think now this is where I need the 1. That's where I need the 1. So let's try this. Let's try this. I think this will work. Let's use this. I think this will give us what we need. So now, if we use our formula, x prime, and notice here, and this is what's interesting here about this. If I try this, then we can integrate on 0 to pi over 2. Because at pi over 2, we would get that point and we would just integrate between the cusps. So we can integrate here and then multiply result by 4 to get the complete length of the curve because it's all symmetric. Let's try this. So let's do x prime. So this will be an a, and we get a 3 cosine squared theta times a negative sine theta. So this gives us negative 3a cosine squared theta times sine theta for x prime. And then y prime, let's see, we've got an a, so that'll be a 3 sine squared theta times a cosine theta. And that'll give us a 3a sine squared theta cosine theta. Now we need x prime plus y prime. So here, x prime squared plus y prime squared will now be, let's see, that's going to square this out. So we'll get a 9a squared out of both of them. Cosine to the 4th sine squared plus 9a squared sine to the 4th cosine squared. So that'll reduce very nicely. So what we'll do is we'll take out a 9a squared and 2 copies of cosine and sine. So we'll have cosine squared theta, sine squared theta, and that leaves behind cosine squared plus sine squared. But that's just one. So this gives us 9a squared cosine squared theta sine squared, which is a trig integral we can do. And of course, a is positive. So yeah, this will work. This will work. This will work. I mean, now I can see that this actually will work if I take this curve and parameterize it this way. So this does actually work. So now arc length using this will be 4 times this integral, 0 to pi over 2, and then we take the square root 9a squared cosine squared theta sine squared theta square root d theta. So now, right here, but now we're just using theta instead of t. So this gives us, well, we'll get a 3a out of this, the absolute value of a being the square root of a squared. And of course, that's just a hypothesis. So that's a 4 times a 3a, 0 pi over 2. So this will give us the absolute value of cosine theta times the absolute value of sine theta. Again, the square root of the square by definition is absolute value. This is good. I'm glad yeah, sometimes living on the edge, Professor Ron, but this will work. So now notice here for this interval of integration, which is simple, it's in the first quadrant. These are both non-negative, so we can remove the absolute values. So this will be, let me write it here, 12a, 0 to pi over 2, sine theta, cosine theta, d theta. Reason I'm writing this way, because you can do these a million different ways, but when I teach trig, I always like to use identities that we don't use as much. Let's use the double angle. Remember, we use this a lot. Sine 2 theta is just 2 sine theta. You could do the du, but this is fun. Use that. So we'll have 1/2. So this equals 12a divided by 2 integral 0 to pi over 2 of sine of 2 theta d theta. So this gives us 6a. And then, of course, we need the 1/2. The antiderivative of sine is the negative sign. So we've got the divide by 2 because of the 2 there and the negative. So that'll be a cosine 2 theta from 0 to pi over 2, just like we're back in chapter 8. So that's a negative 3a. So cosine of pi minus cosine of 0. So that's a negative 3a. And of course, that's just a -1 minus a 1. So that's a negative 2. Good, it does work, 6a. So this wasn't completely off base. This does work. A little sketchy the way I tried to provide a equivalency between the two, but this does work because that's the answer we got before. So absolutely. So now we're thinking, you know, if you were stuck with this and you didn't make the connection to here, that would be unfortunate because again, you have to be able to make sure that you understand what the curve is doing, especially where is it smooth, where is it not smooth. So that's what occurred to me when I thought about this, and I wrote this up in the lecture notes. This is a very nice problem. So yeah, nice problem for a final exam. Now, let's look at one more thing that we need to do, which is you have this surface area deal, and what do we have to do to make that extension? And it's actually very simple. So again, what I've written here is we all often think about the surface of revolution, where we take a curve and we revolve it about either the x-axis or the y-axis. So let's do the same thing. We'll say r of t equals x of t, y of t. And if you like, we can think even more simply now. We can just go ahead and use again another alpha beta or AB, whatever, alpha beta. R is smooth. So we want the same hypothesis we had for the arc length. So the idea is all we have to do is tack on the distance to either axis and then our arc length formula. So there's no additional work to be done here. We did all the hard work with the arc length. Let me touch up the move Professor Ron over a little bit and touch up the focus. There we go. I just have to be careful not to click outside the box. You know what happens? My IPvo goes away. So now, we've got the element of arc length, which we can use to find the little piece, rotate about a given axis. So now, number one, let's just say here what I've written: revolve R of t about x-axis. So again, the distance to the x-axis from the parametric representation will just be y of t. So this implies that our surface area formula, now everything's the same, except now we just substitute the element of arc length, which is what we derived earlier. So we have, in this case, y of t, distance to the x-axis, and then the element of arc length. So I'll just do it x prime squared within the lazy notation, forgive me, y prime squared to the 1/2 dt. Okay, so we've done all the work, we just have to make the extension to what we derived earlier. So that's very simple. And then number two, we can revolve R of t, the parametric representation, about y-axis. And this is when it's convenient to actually know the orientation of the curve and how it's distributed via the axes. So this will give us S. Now the distance to the y-axis will just be the x-coordinate. And we've done this many times before with the center of mass, our friend center of mass. Those were fun calculations. X of t, x prime squared plus y prime squared, 1/2 dt. So now what we're seeing is that we have this new formulation for arc length. We can just simply extend the area of the surface of revolution with that new element of arc length. And here's an interesting little problem I found on WebAssign that I want to use. Always find interesting examples or make up some. So here's an example. And I love cofunctions, they're fun. So a portion of a sphere, I like the way this is worded, a portion of a sphere of radius r, a portion of a sphere of radius r is removed by cutting out or excising, if you're a surgeon, excising a circular, I guess that would be better for your English professor, excising a circular cone with its vertex, this is doable, with its vertex at the center of the sphere. So again, it's symmetrically distributive. The vertex of the cone forms an angle of 2 theta. So they gave you nice numbers. Then it says compute the surface area removed from the sphere. So when you think about this, this is the sphere, the great circle is just a circle, and you're thinking, well, that's easy enough. So first, I thought this was kind of neat. We can think about the revolution process, but let's just draw that part of the sphere. So we'll do, let's see here, radius R. So pictures are always nice in calculus. I mean, let's face it, we do like our schematics. So now we've got this cone. The vertex is right here at the center. And so we could just draw it. Let's just, theta on either side, 2 theta, symmetrically distributed. So that's theta. And then here, we'll do the same. Why do you have to know calculus to do physics and engineering? Because that's all you do in physics and engineering is calculus and all that extra stuff. And so now you want to remove this, you want to excise it. So you're thinking, okay, this is the piece that we need to revolve. That's how much is cut out of the surface. And so if you think, you can say, well, we're already using a theta here, so I just used a beta, R beta, and I'm sorry, let me just call this big R because I use little r, yeah, R beta, because the radius I don't want to reuse, even though I know your physics professors tell you you have to get used to it. So R cosine beta, R sine beta is just a circle. Now, when you think about the situation about, okay, so this is theta, so we're running this way. So as we move all the way up here, let's just mark these off. We move all the way up here, that's pi over 2. And we want, let me just extend this a little bit. We want to do this. Because if we revolve this about the x-axis, we're getting that little cap that's going to be excised. So we can find the surface area here as a surface of revolution just by revolving the circle. And then we get that little dome, partial dome, so to speak. But here's where the cofunctions come in. Notice the angle here. I love the cofunctions. Well, I love math, but I love the cofunctions. This is going to be pi over 2 minus theta. Right there. So this is a nifty little problem that's actually quite doable with the parametric representation. So now let's just say, okay, so we need to revolve this, and we've got the distance to the axis of revolution in this case, which would be the x coordinate. But first, let's go ahead and do the primes and all of that. So we have x prime would be a negative r sine beta. We're integrating or differentiating with respect to beta. And y prime will be r cosine beta. So now, if you will, and this is where we have to think about the fact that when we actually work this, what do we get? So let's do our computation. X prime squared. This is a lot easier than the last problem we did. Y prime squared will be, square this out, the negative goes away, r squared sine squared beta plus, we'll do this a lot with polar coordinates. That's why I'm spending so much time on this. I know I'm being very meticulous about this, but this is extremely important. So that's just r squared times 1, right? So that's r squared. So this is r squared times sine squared beta plus cosine squared. That gives us this. So now when we take the square root, we'll just do all the work on the little sidebar here. That'll give us the absolute value of r, which is just r. Square root of r squared is the absolute value of r. By hypothesis is positive. So boom, right there. So now S, we want to revolve this about the so-called y-axis, if that's how we've oriented it. I've written it this way. I mean, that's the way I see it. So this will be what? So we're integrating from pi over 2 minus theta to pi over 2, pi over 2 minus theta to pi over 2. And then, of course, for element of arc length here, the distance to the axis of revolution is r cosine beta, times the element of arc length, which is r, d beta. So element of arc length, distance to axis of revolution, we're good to go. So this gives us, oh, and of course we need our 2 pi from the definition. Don't want to leave out the 2 pi, don't want to discriminate. So that'll be 2 pi, take out the r's, r squared. So we have the integral pi over 2 minus theta. Remember, theta is the given constant. And we're left with a cosine beta d beta. The antiderivative of cosine is the positive sign, what you learned in Cal 1. So we get sine beta pi over 2 minus theta pi over 2. So this gives us 2 pi r squared. So we get sine of pi over 2. Of course, I had to choose another variable because, you know, we're already using the theta here, so it looks a little odd. Minus sine of pi over 2 minus theta. That's the cofunction. Okay, so that's cosine theta by the cofunction identity. So this gives us 2 pi r squared. Of course, sine of pi over 2 is 1. And then the cofunction, cosine theta. So I keep using cofunctions, but remember, it's just like saying sine pi over 2 minus x equals cosine x, etc. Cosine of pi over 2 minus x equals sine x. The same for cotangent, tangent, secant, cosecant. The cofunctions are extremely important. But now that you can see here, we get a rather elegant solution right here, just using the concept of surface of revolution. I thought this was an interesting problem. I was looking through the WebAssign because, I mean, when you just work with a sphere, that sphere's not really very challenging. I mean, we do a lot with spheres, but what made this problem, it reminded me of when we, you know, took made a ring and then used the Chapter 7 techniques to figure out the volume of the ring. That was a very non-trivial problem. And this one kind of reminded me of that, but instead of removing the cylindrical type object, we're removing this. And so it's not necessarily a solid, but when you remove this part here, thinking of it, the part of the surface that's removed is this. And so we can just think of this surface here as a surface of revolution, and very simply using the great circle. And notice I only wrote half of the great circle here because that's all we needed, because the vertex of the cone is at the center of the sphere. So this is a really nifty problem. And again, what I wanted to show you today, especially, you know, when we think about computing arc lengths, we're just doing trig integrals. We're just doing trig integrals, simple trig integrals that we know how to do very well because we did chapter 8. But the beauty of all of this is that when you get to Cal 3 and you start talking about curves, this parametric representation will be indispensable. And one of my favorite classes in grad school was differential topology, where we did differential geometry on surfaces and on curves. And it's an amazing study. And those of you that like your physics, that are going to go into maybe nuclear engineering or electrical engineering, especially the nuclear engineering, that seems to be a really popular engineering field with some of my students. The ones that really like math, they said, Professor Ron, we love the physics, and they love how the mathematics innervates all of this. So what I wanted to do today, ladies and gentlemen, is just basically develop the calculus of the parametric equations. And so now you'll be able to take this and then extend it in Cal 3, and then eventually in differential geometry. So what we're going to do after the break is talk about polar coordinates. So we're still going to be doing trig, but we're going to now think about curves represented with polar coordinates, which isn't this. It's still different from this, but there are lots of similarities. So I wanted to give you enough information here so you can distinguish the two. So when we start talking about polar coordinates, that's just another way to parameterize, so to speak, a curve, but you've got two coordinates. You've got the r and the theta. So it's different from this, but similar. And so we'll work with the polar coordinates. It's be like we're in pre-cal, you know, trying to figure out how to graph them in a way that makes sense using the Cartesian graph. So we'll toggle back and forth. And then after we do all of that, it's going to be the same thing we've done here. I introduce parametric, then we do the calculus. I introduce polar, then we do the calculus, and we'll do the same thing that we've done with the parametric representations. So you'll find uses for each of these, but you'll have to be savvy enough to decide when you need to use it and where it will actually make sense in the particular problem. This is an interesting example here. It's the way I interpret it. It's certainly not the only way to interpret this problem, but I interpret things in a way that has to do with the mathematics I teach you. And I don't like to stray too far from it because there's got to be some synthesis. So what I'll do today, I'll go ahead and get up the test number 4 work tab on Blackboard. So do your planning, get your studies done, and make a good time to take your Calculus 2 test. And be sure once you're done, get your paper scanned and get those submitted, and you'll be in good shape. Like I said before, I've given you that extra day that I always do. So if you have plans or whatever, then you've got the time to go ahead and work it in a little bit earlier on Tuesday. But a lot of students were telling me they'd appreciate an extra day, and I'm all for that. I just don't want to impinge on any of your plans, but I don't want you to feel like you're pressured. I like to give you plenty of time so you can plan and plan with your other classes. So I appreciate your attendance today. This is some really fun stuff. Hopefully it was somewhat enjoyable to have a walk down trigonometry lane. I really enjoy trig and how it innervates the calculus, and it's a lot of fun to have a nice change. So stay, I was going to say stay warm, but I don't know what Mother Nature's going to do to us. Who knows? Of course, I was cold this morning, but tomorrow it may be 90 degrees. Who knows? But have a good day. Good luck with your studies. If I don't see you at the conference hours, then I wish you a very happy time off. Don't get too lazy. I mean, take a little bit of time off, but keep that engine running so that you're ready to keep that mind firing so you can finish up the term. But be safe and take care as you go out to wear your mask. We'll see you later, everyone.
Thank you, Professor Ron. Have a good day.
Bye.